Good day, good evening, I don't know, to everyone. It is my pleasure to give you this overview about machine learning in geotechnics, and I would like to thank, of course, the organizers for giving me this opportunity. So don't expect me to give you a kind of state of the art. The time is too short. And I will focus on some issues and some particular topics that I think illustrate the trends in applying machine learning in geotechnics. But let me start with some general comments. And first, what we usually associate to machine learning, which is its application for the study or the modeling of complex systems. I show you here, well, on the left, you have slides that I showed a few years ago during a conference in France. It was about recent advances of machine learning for geosciences, and one of the applications that I mentioned more particularly was the improvement of weather forecasts, and the value behind it was for Google teams to improve the forecast for wind and in particular to sell better the energy associated to wind farms. A few years later, the same group, still from Google, published this paper. It was in 2023, last year. I think it was exactly 1 year ago. Published in Science, and it's about the use of graph neural networks. The tool is called GraphCast, and they more or less, well, the application and the power of this tool is quite impressive. I just give you a few words. So it's based on discretization of the atmosphere in small blocks. At the level of the equator, it's about 28 by 28 kilometers. So it's quite refined mesh. And over the atmosphere, in the thickness of the atmosphere, they mesh it in 13 layers. They provided historical data to the graph neural network. And so they ask it to predict for a given state, the next state, and then to roll out for a complete forecast. The computation is lasting less than 1 minute compared for a deterministic model for the same kind of simulation to a computation time of 6 hours. So it's quite impressive in terms of computation time. And if we look in more or less detail, this tool, GraphCast, is better than the state-of-the-art predictive model in 90% of the cases. And if we exclude the 2 last layers of the atmosphere, the top ones, so close to the space and not to the Earth, the accuracy of the tool is 99.7%. So you could say, okay, you are giving us figures in average and saying that the tool is good in average. But they investigated some specific features, and the tool was better to predict the trajectory of cyclones, atmospheric rivers, and extreme temperatures. So this is quite impressive for very, very complex systems. So we are talking about complexity. I like very much this drawing by Randall Munro for the New York Times. And you see that we are standing at the end of complexity with the sand that we use. And I would add that if we study clays, it would be even worse. So why not using artificial intelligence for our geotechnical applications? And actually, this is the case. You see here in the literature, so you have at the bottom of the slide, you have the request from Scopus that I run yesterday. So it's updated. So I looked for keywords in title, abstracts, or keywords related to soil mechanics, geotechnical engineering, and geomechanics. And associated to these keywords, some keywords associated to artificial intelligence. You have them here, machine learning, etc. And you see that the publications are not new. What is new is a very fast increase in the last decade. And if we put some moments associated to this trend, I put for memory the episode of Deep Blue, which is not exactly machine learning because they used a lot of brute force, but still it's kind of beginning of artificial intelligence in the media, not in reality. This is much older, dating back to the 50s for the theory and first applications. Then you have the big bang, I would say, of deep learning and the use of structured databases and graphical processor units. And then still in the media and the public audience, the arrival of AlphaGo and when it beat the world champion, one of the world champions of Go, I think it was in 2017. So yeah, this is for the background. So what has changed? As I just mentioned, in recent years, we have more advanced algorithms. The first example I gave you about weather forecast is an example with the graph neural networks. We have more computational power and hardware that is dedicated to machine learning, like NVIDIA cards, for instance. And we have more and more data. If we look at what we have or what we need in geotechnics, of course, we all would like to have faster and cheaper design for our structures. We want to learn from the data that is available. We would like, in particular, to enrich empirical approaches, to design alert systems that are more efficient, and to improve our maintenance of infrastructure, for instance, for a more predictive maintenance. And of course, in the context of climate change, we would like to account for new phenomena or new physics. And so all this adds to the complexity of our systems. So I will not enter into the detail. We have too many things to discuss, but in terms of learning modes, we have this classification that is usual, supervised learning, unsupervised learning, reinforcement learning, with all sub-classification that you probably all know or heard about. I will not define all these terms. In terms of use of data, we have also several categories. We could start and live with a fixed data set, but of course we can also think of applications where the data set is constantly evolving with new data coming from sensors, for instance. And this will give different applications. And in terms of generalization, I will come back to this, but I put here classifications in terms of how we train our models. So based on pure data, real data, let's say, if we add some physics to constrain the learning, or if we simply start from an already existing model, for instance. So let's start by the data. And I will give you two different applications where we started at École des Ponts from completely different data. We have the PhD work of Tatiana, who is here, hosting the seminar. So we have been lucky to have a very large data set of displacement and TBM data coming from the excavation of two lines of a big tunnel project in the Paris region. We have 16,000 sensors, for instance. Of course, you lose some data after cleaning, but with measurements every 30 minutes, for instance. And here you have an example. I will give you an application afterwards, but the other point, the other end of the paradigm about data It was for a PhD looking at the evolution of landslides, and in that case, we chose to start from a model, an existing model fitted to a particular landslide, and we generated data using this model, and then trained a model, an AI model, a machine learning model for predicting the outcome depending on the weather conditions for this particular landslide. So let's start with this and the preparation of the data. I think this is one of the key aspects when you want to dig into machine learning. So you have to know your data. If your data set is large and you already know that you will valorize and use significantly this data set, you be well inspired, as Tatiana did, to create a structured database. I will not enter into the details, but the PhD is available online, and you could, even if you would have to translate it from French, but you would find a very nice description of what is required in terms of methodology to set up a complete approach. So I will pass on that, but cleaning, thinking of the accessibility of the data, and of course preparing your data for the machine learning aspects. So what was done in Tatiana's PhD, we end up in a kind of proof of concept with the aim to predict in real time the maximum settlement induced by excavation. So you have here a schematic of the philosophy we adopted. So we trained our algorithm based on the data behind the tunnel. So you have here the tunnel with the front of the tunnel, excavation front, and we give the machine learning algorithm data that is quite back from the front. Let's say all data, 100 meters behind the front. And we ask the algorithm to predict what is expected in front of the excavation front. Using random forest learning, what we have shown is that if we give the algorithm 5 months of borrowing and training the algorithm on this particular data, which corresponds to more or less 500 meters of excavation, we are able to predict with acceptable precision 150 meters in advance of the excavation front. If the training were for 8 months, we were able to predict 300 months in advance. So this was quite satisfying. I'm showing with you quickly the other application about landslides, and I described it in a few words before, so I will go quick on that. We used LSTM, which is particularly well suited to time series. And so, as I told you, we run the model and we run the real model of the landslide to generate data. We train the LSTM network on that, and then giving 180 days of data history, we were able to predict with weather forecast what would be the future of the landslide over 15 days, and with a quite satisfying precision in that case too. Okay, so in this case, and the landslide problem was a particular example, we end up with what we can call surrogate models, and we have trained models that are much more rapid in giving their predictions. This has been done more specifically also still in our lab in a PhD that was defended very recently by Alec Tristan. They used also a numerical model to generate data. It was the excavation of a tunnel with a support that you see here. It's small, but you see the support here. And the idea was to predict the pressure and the radial displacement on the support. the method that was used is using an ensemble method and artificial neural networks. What is interesting is that you see that if you use a bagging approach, using this approach, you end up in predictions that are much better than using a single model that would have seen the complete data set. So this was an interesting result of the PhD. Another example, I will not give the details because it will take too long time, but it's to refer back to complexity.
I think we're having an internet problem.
Can you hear us, Jean Michel? Can other people hear us? Yes, I think so.
Yes. Yes.
Okay.
Yes.
I think Jean Michel had an internet problem. Let's wait some more seconds, and if he gets connected back, if not, we propose to move to the next one.
And if people already have questions, don't hesitate to put them in the chat. That way we can amend it.
Yes, I think we lost Jean Michel. Son numéro. Je fais un SMS en disant connexion coupée. Ah.
Yes, Jean-Michel, I think you had a connection problem.
Can you hear me?
Yes,
Yes.
now it's good.
Yeah. I'm sorry. Teams completely crashed.
It happens.
It's like the blue screen, but on a Mac. Sorry for that.
No worries. And we're having questions that are coming in the chat. We'll let you finish your presentation.
Yeah, go ahead, and then by the end of the presentation, take some questions on the chat.
Yeah. Where I was when it crashed?
Geothermal.
Yes, so it was, yeah. Okay, so I just need to share again. So do you see the screen?
Yes.
Yes, it's good.
Okay, so I was saying that the input data was quite complex, and they accounted for the computational fluid dynamics inside the tubes, generated data, and then trained an artificial neural network to predict the temperature and design the geothermal pipes. Quickly, because I'm late, the question is how to account for the physics if we know the physics of the problem, and we have solutions for that. One example is physics-informed neural networks, where you encode some equations, differential equations, for instance, inside your neural network, and account for it in the cost function, so as to train knowing more or less what you know, and what the physics at play. And so here it is an example of a paper by Raoul Fontes and co-workers, where they estimate the temperature within the shear band of a landslide. Another example, but at a smaller scale, at the material scale, so it's thermodynamics-based artificial neural networks. And so there, they want to, by Massy and Yannis Stéphanie, they want to generate constitutive laws, and they compute the dissipation, the mechanical dissipation, for instance, and they have a complete thermodynamical framework to constrain the data. The main advantage of these two examples I'm giving is that this kind of models are much better at generalizing the predictions, and in the case of Massey's work here, they can even extrapolate beyond the range of the data that was provided for the learning. I'm just finishing with a last topic quickly. It is about generative artificial intelligence. I search on Scopus. It's not much used in geotechnical engineering, but I think it's a line that would be followed in the coming years. Here, it's a work I've done with a former PhD student and colleagues from Australia. So Zhongzheng Wang developed a model to predict two-phase flow at the pore scale. So here you have grains in black, and what he's able to do is to predict the injection of a gas, for instance, inside a pore network, and it simulates the flow paths up to the percolation of this phase. And then it trained with this kind of data generative adversarial network, so that is able to generate new images, and then he compared these images. Of course, the computation is much quicker, and the performance of the model was quite satisfying also. I found a few examples in geotechnical engineering. Here it is one of these examples. So what they want is to generate when you don't have enough data from boreholes, and when you want to generate a geotechnical profile, for instance, they use the same kind of approach, JNN, to generate new boreholes. And if you continue this approach, you will generate a complete soil profile. So yes, this is more or less the end. I finish with this image that I like very much. So our models that are based on the data that generate themselves are like these robots that are using the structure they are printing to continue printing this footpath. It's a real footpath. So yeah, we need to trust what we are predicting, and this is my final slide. Trusting this, what we predict is based on would require interpretable and explainable machine learning algorithms. I have no time to discuss that more, but this is something that is in my mind. I think, in my opinion, it is very necessary to diffuse our research and our work to a broader community that would use it on a daily basis. And two keywords: know your data, know your model. It's not a model is not a model per se. You need to add reflection, design, and decision to that, and train also students and colleagues to have a diffusion of these tools to the community and engineering in general. Thank you for your attention.
Thank you, Jean Michel. We're going to take one question from the chat. How did you implement the provisional geological model into the machine learning model to evaluate the settlement induced by TBM?
I'm not sure to have listened.
How was the geological model taken into consideration, the features?
Oh yeah. Well, it was complex. We had to combine the data. Of course, the difficulty is in the number of layers when you advance the tunneling, the excavation, and so the strategy that Tatiana found was to combine the different parameters of the geotechnical profile that we knew in advance. And this is something known from the geotechnical campaign. And so we combine this data in a single vector to provide to the machine learning algorithm.
Thank you, Professor Pereira, for that comprehensive overview.
Sorry for the bug.
No problem.
Next, I'm pleased to introduce Dr. Stephen Surya-Santana from the University of Strathclyde, Scotland. He will discuss the applications of machine learning in offshore geotechnical engineering. Dr. Surya-Santana, the floor is yours.
Okay. Can you see my slides?
Yes, perfectly.
Okay.